class, we've been learning about how electrons are arranged in the electron cloud. In this video, you're going to learn to write orbital diagrams and electron configurations which symbolize how those electrons are arranged inside the electron cloud. That's what you should be able to do after watching this. We're going to start with an example. In this slide right here, you can see that there are a bunch of elements listed. The top one here is lithium, which has 3 electrons. Those 3 electrons are arranged in the electron cloud according to the electron configuration, which is written here, and according to the orbital diagram, which is written here. In the orbital diagram, an arrow, either up or down, refers to an electron. So each arrow is an electron. You can see that there are 3 arrows, so there are 3 electrons. Those electrons are represented over in the electron configuration as superscripts. So that refers to the fact that there's 1 electron in the 2s orbital, the 2s orbital being the box, and this referring to the fact that there are 2 electrons in the 1s orbital. So there are 2 arrows in the 1s box. All right, you should remember this, what showed up on the green here, that in this configuration, in the electron configuration, the big number in front, the coefficient 2, refers to the energy level. The P represents the sublevel or orbital type, and the 4 represents the number of electrons. If you noticed, that actually is what's in oxygen. So the fact that it says 2p4, it means there are 4 electrons in the 2p orbitals of oxygen. Each orbital can only contain 2 electrons, but since there are 3 orbitals, it can contain 6 at most. Oxygen only fills 4 of them, or 4 electrons in those 3 orbitals. All right. The orbitals fill according to the rules that are listed here: the Aufbau principle, Hund's rule, and the Pauli exclusion principle. I can summarize the Aufbau principle, Hund's rule, and Pauli exclusion principle a little better than the wordy writing that's here. Aufbau principle just means lowest energy level is filled first, or lowest energy orbital is filled first. Hund's rule says if there are orbitals of equal energy, spread out before pairing up. In other words, electrons repel each other, so you should get 1 electron in each orbital before you start putting 2 electrons in the same orbital. That only happens when there are orbitals all at the same energy, though. The Pauli exclusion principle says that the second electron in any orbital has to be spin down. If the first one's spin up, you can only have 2 electrons in the same orbital if they're opposite spins. Remember, electrons repel each other. If they're the same spin, they just simply can't be in the same place at the same time. All right, let's go back to the example. So you can see right here that the Aufbau principle is in evidence because the first energy level, 1s, is filled first. That's the 1s orbital is the very first one filled in every single orbital diagram. Every single element here fills the 1s before going up. And you can also see in the orbital diagrams that they're filled left to right because this is the order of increasing energy. That as you go from left to right, the energy of the orbitals increase. Hund's rule is shown in the p orbitals because Hund only works if there are orbitals all of the same energy. And the 3 p's are all of the same energy. So you can see in carbon that there are 2 electrons in the 2 p's, but they're in different orbitals because since the orbitals are all the same energy, the electrons want their space. Notice that this doesn't work back in beryllium. In beryllium, you have 2 electrons in the 2s instead of one of them going in the 2p because the 2p would be too high of energy, so you can't have that happen. Finally, you can see the Pauli exclusion principle because whenever 2 electrons are in the same orbital, 1 spin up and 1 spin down. All right. The only rule that you can really see in the electron configuration here is the Aufbau rule, but the Hund's rule and Pauli exclusion principle are both happening. It's just that we don't write any indication of them down in the electron configuration. So electron configuration is kind of like a shortcut for the orbital diagrams. All right, this is the order the orbitals fill. This is how we follow the Aufbau principle. All right, you do not need to know this. You do not need to memorize this diagram. It will be given to you on any test or quiz. You need to know how to read it. The way it works is every single electron in any single atom starts at the 1s orbital. The first electron always goes in 1s. And then after the 1s is filled, you reach the end of this arrow, you have to go to the beginning of the next arrow. And the very next energy electron is going to go in the 2s. And then after 2s, you go to the next arrow, and the next electrons go in the 2p, and then the 3s, and then the 3p, and the 4s. This is what happens when you fill multiple electrons in atoms. So hydrogen only has 1 electron, but oxygen has 8, and then bromine has 35. You have to use this diagram to get the electron configurations that are displayed here. So since bromine has 35 electrons, we have to fit 35 electrons in the atom, and we always start at the 1s. I'm going to trace it through right now. So remember that S can fit 2, P can fit 6, D can fit 10, and F can fit 14. You do have to remember that. So 1s, the first electron in bromine out of the 35 here, has to go in the 1s. You can fit 2 electrons there. Hey, look, we got 1s2. After we get to the end of this arrow, we go to the beginning of the next arrow. Now we get 2s, and we can fit 2. Then 2p, we can fit 6 in 2p, because the p's can fit 6 electrons, because you've got 3 different orbitals. Then the 3s, then the 3p, then the 4s. As of this point, 4s2, you have 2, 4, plus 6, that's 10, plus 2 is 12, plus 6 is 18, plus 2 is 20. This point has 20 electrons so far. As of this point on the chart, we've gotten up to 20 electrons. Bromine has 35. We've got 15 left to go. Let's keep putting them in. 3d, 10. Oh, look, now we got another 10. So we're up to 30 electrons now. We only have 5 more to go. Those are going to go in the 4p. So we're going to put 5 more electrons in. That's why 4p ends with 5 instead of 6. We only got 5 electrons left. All right, this is the orbital diagram, so we could just as easily draw how bromine fills its energy levels by using boxes like this. If we've got 35 electrons in bromine, we have to put all 35 arrows in, starting with the bottom because that's the off-bow principle. That's the first electron, the second, the third, the fourth. Remember, fill lowest first. That's the off-bow principle. Then we get up to the 2p's. We have to spread out before doubling up. So the next 3 go like that. Then the next 3 have to double up, pair up, before we can move on to the next energy level. That's the off-bow principle again. 11th, 12th, 13, 14, 15, 16, 17, 18. All right, now we get to the next energy level. The 4s is actually lower than the 3d. So we have to fill the 4s before the 3d. Why? It's just how it is. So now we've gotten 20 electrons, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. We've got 30. We've got 5 left to go. 1, 2, 3, 4, 5. That's 35 electrons. Notice in bromine, the last orbital is unpaired. All right. It ends up that these electron configurations line up very, very well with the periodic table. And this isn't by accident. Every element that has an S on the end of it is over here in the S block. Every element with a D as the last electron is in the D block, which is here. Every element with P as the last electron is in the P block right here. And every element with F as the last electron is in the F block down here. The neat thing is, instead of counting all the electrons, which is what we've been doing, we instead can just use the location of an element on the periodic table to write out the whole electron configuration. Let's use bromine again. All right, it ends up energy levels correspond really nicely to the rows of the periodic table. We know that this is the S block, this is the D block, this is the P block, and this is the F block. So those are going to be the letters. And in every block, this is the number of electrons in the element. So 1, 2, 3, 4, 5, 6. All right, so here's how it's going to work. Find bromine on the periodic table. It's here. I'm making it kind of dark so you can see it. All right, that element, bromine, is in the 4th row. So it's going to start with 4. That's the energy level. It's in the P block. So it's going to have a P as a letter. And it's in the 5th column. So it's 4p5. And that, in fact, is what the electron configuration of bromine ends with. You got to be a little careful over here with the D's, because with the D's, it ends up that you can't exactly go by the row numbers that you can with S's and P's. The row number for D here, these are the 3 Ds over here. And these are the 4 Ds and these are the 5 Ds. It's one off the row number. Also at the bottom, these are the 4 Fs and these are the 5 Fs. Just be careful with the transition metals. Right, noble gas electron configuration is a shortcut way of writing electron configuration. Instead of writing the whole thing out, which by the way can get very, very long, you can write a shortcut method. The way you do that is you set aside the core electrons, which are the electrons on the inner energy levels, the full energy levels, and you say, okay, those electrons don't really do anything in the atom. The only ones that do anything are these ones on the outside. It ends up that the core electrons line up really well with the noble gases, which are the furthest out elements to the right of the periodic table. What I mean by that is that this electron configuration of the core elements is actually the same as the electron configuration of neon, which means instead of writing all this stuff at the left, I could just write Ne in brackets. So instead of writing this part of the electron configuration, I can just write Ne and then pick up from there. This is really helpful with uranium. This is the short version of uranium, whereas the long version of uranium is really, really big. And this is a little helper slide to show you that instead of writing all of this, you can just write Rn in brackets. It's really helpful. Or Xe in brackets, or Kr in brackets. Good thing to point out is you can only do this with noble gases, no other elements. Only noble gases can go in brackets. All right, so let's look at uranium. Uranium has 92 electrons, which means that you're going to be going for a while. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, messed up on that one, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2. I'd just like to point out, as of 7s2, we've gotten up to 88 electrons, which means we only need to put 4 more, which means 5f4. So the whole thing for uranium ends with 5f4. And if we do out the whole electron configuration of uranium, it does in fact end with 5f4. Or we could have just looked at the periodic table and known it ended with 5f4 and keep filling it in until we get to 5f4. Right, it ends up, that whole beginning part is the same thing as radon. So instead of writing the whole thing, we can just write Rn in brackets, 7s2, 5f4. Right, this is another shortcut way of writing the electron configurations. You can use that periodic table method we were talking about. This is an example for arsenic. You find arsenic on the periodic table. You go up into the end. That's argon. This is the noble gas that you put in brackets. And then you pick up from there. The next element is in the 4th row of the S block. And you go over to the 2nd column. So that means it's 4s2. Then you keep going. This is the 3 Ds. And you go all the way to the 10th 3D, which is zinc. So you're going to write 3d10. And then you keep going until you hit arsenic, which is in the P block, the 4th row. It's 4p3 because it's in the 3rd column. And in fact, that is the electron configuration for arsenic. Thank you very much for watching.